A 7-year-old male mixed breed dog tests positive for disease X. You, the veterinarian, want to know whether the dog truly has the disease or not. The owner is not present. You know that the prevalence of disease X in the dog population in your area is 1%. The test done on the dog has a sensitivity of 90% and a specificity of 91%. Of the dogs that test positive for disease X, how many truly have the disease? A. 9 in 10, B. 1 in 10, C. 8 in 10, or D. 1 in 100? You may pause the video and try to figure this out for yourself first. I encourage you to. Okay, now that you have your answer, hold on to it, and we'll return to this later. Let's have a little review first. We're going to make a table. On the left side, we have those that have the disease and those that don't. On top, we have the test results we can get. If you test positive and truly have the disease, that's a true positive. If you have the disease but tested negative, that's a false negative. If you don't have the disease but tested positive, that's a false positive. If you don't have the disease and test negative, that's a true negative. The prevalence is the number of patients that have the disease over the sum of those that have the disease and those that don't, or pretty much the total population in the sample problem. Sensitivity, also known as true positive rate, is the number of true positives over those that have the disease, or the number of true positives divided by the sum of the true positives plus false negatives. The specificity, also known as the true negative rate, is the number of true negatives over those that don't have the disease, or the number of true negatives over the sum of the true negatives plus false positives. The false negative rate is 1 minus the sensitivity. You can remember this because true positive rate and false negative rate are kind of opposite. True positive, false negative. Okay? And also the other way around, which is the false positive rate is 1 minus the specificity. Same thing. If you've noticed, all of these are probabilities. So let's have a little review about probability. So as a review, the probability of event A is equal to the number of times A occurs over the total number of outcomes. Think of those probability examples with the coin flip, the dice rolls, the deck of cards, those things. Union probability, or the probability of A or B occurring. This is equal to the probability of A union B, which is equal to the probability of A plus the probability of B minus the probability of A intersection B. We'll get to what this is later. If A and B are mutually exclusive events, the probability of A intersection B is 0. Therefore, the probability of A union B is equal to the probability of A plus probability of B. The probability of A and B is the probability of A intersection B, which is equal to the probability of A given B has occurred multiplied by the probability of B. Or the other way around, the probability of B given A has occurred multiplied by the probability of A. If A and B are independent events, the probability of A given B is equal to the probability of A, because it doesn't matter whether B occurred or not. And we could also write that the probability of B given A has occurred is equal to just the probability of B. This is if they are independent events. But the events in our sample problem are not independent of each other. So let's look at conditional probability. The probability of A given that B has occurred is equal to the probability of A and B over the probability of B. There's also negation probability, so the probability of A prime is equal to 1 minus the probability of A. This can also be denoted with the squiggly line or this symbol. So in some texts, this is how they are written. Okay, are you still with me? I introduced these concepts in probability because prevalence, sensitivity, and specificity can also be denoted like this. Prevalence being the probability of the disease occurring, Sensitivity or true positive rate is the probability of getting a positive test result given that you have the disease. And specificity or true negative rate is the probability of a negative test result given that you don't have the disease. Going back to our sample problem, we are looking for the probability that the dog has the disease given that he tested positive. This is not the same as the probability of testing positive given that he has the disease. That's just the sensitivity. So if you answered A, then that's incorrect. It is a very common misconception that a positive test result means that the patient has the disease. The test result on its own also does not tell you the probability the patient has the disease. What the test does is update the patient's pre-test probability of having the disease. What did I just say here? Let me tell you about Bayes' theorem. I'm excited, let's slow down. So the pre-test probability in our sample is just the prevalence, 1%. This is all we know about this case. So there is a 1% chance that our dog is the one dog with the disease out of 100 dogs. That's our pre-test probability. How do we update this? We take the ratio of the test's true positive rate over the false positive rate. This is our positive Bayes factor. This is how strongly the test updates our pretest probability. So 90% divided by 9% is 10. And we get a 1 over 10. So the answer to our sample problem is, of the dogs that test positive for disease X, 1 in 10 truly have the disease. So over here, we have our pretest or prior probability. This is our Bayes factor, and this is our posterior probability. The formula for Bayes' theorem actually looks like this. The probability of our hypothesis given the evidence is equal to the probability of the hypothesis times the probability of the evidence given the hypothesis over the probability of the evidence. If you've noticed, this is just a formula for conditional probabilities expanded. And usually you have to expand the denominator to include the probability of the evidence given the hypothesis is not true. What I used was a redesigned version of the formula I learned from this 3 blue 1 brown video. The sample problem given is also similar. I just translated it to a vet scenario. The question came from Gerd Gigerenzer's paper. It's a very good read, by the way. References are in the description. It's actually more accurate to convert the probabilities into odds. But if the prior or pretest probability is less than 1%, it's okay to do this for quick estimations. I'll show you how to do this with odds. So with a prevalence of 1%, that's 1 out of 100. In odds, it's 1 is to 99. So there is one patient that has the disease for every 99 that don't. 1 out of 100, 1 is to 99. Those are the odds. The true positive rate, or sensitivity, is 90%, or 0.90. The true negative rate is 91%, or 0.91. So our false positive rate is 1 minus our true negative rate, which is equal to 0.09. So the odds of having the disease given a positive test result is equal to the odds of the disease times the true positive rate over the false positive rate. And we solve for it like this. Our Bayes factor is 10. Our updated odds is 10 to 99. Converting this to probability is 10 over 10 plus 99, or 10 over 109, or 0.0917, or 9.17%, which is about 1 in 10. So this is still the best answer. We can check our answers, by the way, by filling in this table. This requires making an assumption though. That's okay. You can visualize it more concretely this way. Say we have a pretend population of 1,000 dogs. So 1% would have the disease, so 1,000 times 0.01 is 10. And then the 99% would not have the disease. So that's 1,000 times 99%, or 990. Okay, that's this column done. Our true positive rate is 90%, so 90% of 10 is 9. And we can fill in this square with the remaining, that's 1. And then our true negative rate is 91%. So that's 91% of 990, which is 900.9. Oh, there's a point here. That's okay. And then for this square, we can just subtract that. So that's 89.1. We get the totals of these two columns, 98.1 and 901.9. Make sure that they all total up to 1,000. Yep, that fits. So our probability of having the disease given a positive test result is equal to 9 over 98.1, or 0.0917, or 9.17%. They are the same. There's 0.1 and 0.9 dogs in this table, so I probably should have made the pretend population 10,000, but the answer is still the same. Bayes' theorem, I think, would be good to use if you want to do quick calculations. And you may check your answers by making a table like this. So it's like a shortcut, in my opinion. Okay, we've been looking at this sample problem for a while now. Let's try another one. This one is a bit more real. Pardon the human med example, but content warnings are on screen. Skip to this timestamp if this topic upsets you. Okay. This is also from the Gigerenzer paper. It's a really fun read. So, at an AIDS conference in 1987, it was reported that 22 blood donors tested positive for both ELISA and Western blot tests. These two tests together have an extremely high sensitivity of 99.9% and specificity of 99.99%. However, in this demographic of heterosexual men with low-risk behavior, the prevalence of HIV is 1 in 10,000. Let's calculate the probability that one could have the disease given they tested positive in both ELISA and Western blot. So our prevalence here is 1 in 10,000, or 0.01%, or 1 is to 9,999. The sensitivity, or true positive rate, is 99.9%, or 0.999. The specificity, or true negative rate, is 99.99%, or 0.9999. The false positive rate is 1 minus 0.9999, or 0.0001. So the odds of having the disease given a positive test result is equal to the odds of the disease times the true positive rate over false positive rate. So we put in the numbers. Our Bayes factor is 9,990. And so our updated odds is 9,990 is to 9,999. I mean, you could look at this and see that, oh, okay, it's very close to 50-50. Converting that into probability, our probability of having the disease given a positive test result is 9,990 over 9,990 plus 9,999, or 0.49977, or 49.977%. So even with positive test results in both tests, an individual blood donor's probability of truly being infected with HIV is a little less than 50%. A coin flip. This case has been documented as a tragedy because 7 of those 22 blood donors met an unfortunate fate. If you've noticed, the two examples we tackled have fairly low pretest probabilities. The disease prevalence is not the only thing that goes into the pretest probability. Ideally, we have examined the patient for symptoms or clinical signs of the disease. This increases our pretest probability by a lot. We also take their history and signalment into account. We don't just run tests just cause. In the second example, the demographics also decrease the pretest probability. Looking at the formula we use, keeping the Bayes factor constant, increasing the pretest probability increases our posterior probability. And the opposite happens when we decrease them. It is a trap to run tests and have that be your only basis for diagnosis. It preys on the illusion of certainty that a test provides. Like, oh, it tested positive, it must have the disease. No. A veterinarian must be wary of this when looking at a patient with non-specific clinical signs. You know, when the differential diagnosis could be many things and you decide to run tests without enough evidence to support that decision. It could lead to a misdiagnosis. And this trap is why. I call this a trap, but I've also seen it referred to as a medical test paradox or a false positive paradox. Let's try a sample problem with a higher pretest probability, so we can end the video on a high note. A 17-week-old male mixed-breed puppy presents to your veterinary clinic. His owner complains of the pup's vomiting and diarrhea in the past week. The puppy is also very dehydrated and lethargic upon examination. Canine parvoviral enteritis is one of your differentials. Among the diagnostic tests you decide to run, a CPV antigen test returns positive. You know this test has a sensitivity of 90% and a specificity of 91%. What is the probability that this puppy has canine parvoviral enteritis? Dogs that present to clinics in your area with these clinical signs have a CPV infection rate of 72.7%. The source is from this reference. But realistically, you would have a rough estimate based on your clinical experience. We're just using this number for our calculations. So anyway, this will be our pretest probability. If you convert that to odds, that's 727 is to 273. There's 727 infected for every 273 non-infected. Sensitivity, or true positive rate, is 90%, or 0.90. Specificity, or true negative rate, is 91%, or 0.91. And our false positive rate is 0.09. So the odds of having the disease given a positive test result is equal to 7,270 is to 273. These are our updated odds. Converting that to probability, we get 0.9638 or 96.38%. So the probability that this puppy has canine parvoviral enteritis is 96.38%. Yay! Wait, not yay. But you can be pretty sure of this diagnosis and proceed with treatment accordingly. Get well soon, puppy, in this example. Okay, to summarize, in this video, we reviewed the conditional probabilities involved in a test's accuracy, and also reviewed some concepts in probability. We introduced Bayes' theorem and how to apply a redesigned formula to determine the probability of having a disease given a positive test result. We then talked about the factors that contribute to the pretest probability and the trap that one can fall into when running tests without sufficient evidence. And we end the discussion with a sample problem that results in a diagnosis we can be pretty sure of. Yay! That's the video! Wow, it's been a while since I've been this excited about a topic. I've been playing with probabilities for a couple of months now. If you're my friend and you've listened to my info dumps, I'm sorry. Actually, no, I won't apologize. You're welcome. Thank you for listening to me. I have so many probability problems that I made up. Anyway, that initial probability problem made me study statistics again to figure out how to solve it. And I learned a few extra things that led to the creation of this video. This was a very fun journey and I wanted to document it. I don't know when I'll be this inspired again. Bye!